there are a few corrections on top of that. One, in particular, in the last problem I see, I realized that the standard, the convention for the Mach-Zehnder interferometer and what the phase shifts are, 50-50 beam splitter was not spelled out and actually not consistent with what we usually choose for a symmetric beam splitter. So that's been corrected. I think for that problem, it's important to go back and review what we studied last semester in the relationship between a Mach-Zehnder interferometer and a Ramsey interferometer. That's to say, thinking about an SU2, what we call an SU2 interferometer, where we thought about the two modes as are sometimes called dual rail qubit, where the two different modes represent the two possible states in a two-state system. It's much easier if you go back and review that, I think. Okay. All right then. So that's what we've been talking about is squeeze states of light, and so what we've talked about so far, what we've emphasized is, what is the mathematical description of the squeeze states, particularly for a single mode of the electromagnetic field. In your homework, you are looking at a generalization of that, what's called two-mode squeezing. We'll talk more about that in different contexts over the course of the next few weeks. But this is for a particular mode of the field. These are the squeezed states that are the pure squeeze states. Generally, they could have some mean field and some fluctuations around that mean, which can be squeezed along some quadrature, okay? And so this was what we call the general squeezing operator, where we have a complex squeezing parameter defined in this way, where the magnitude of the squeezing parameter tells me the degree of squeezing, and the argument or phase tells me the quadrature that is squeezed, okay? And so that is described in terms of the so-called Bogoliubov transformation, which gives me this linear combination between A and A dagger, and that squeezing transformation acts on the phase quadratures to squeeze the quadrature along the direction that's half the angle of this, and anti-squeezes or stretches the conjugate quadrature, okay? So x and p sub theta are the two quadratures relative to the oscillation, relative to some phase, okay? And what we discussed last time is the way that we measure the quadratures, or some particular quadrature, is with a phase-sensitive detector, because this obviously depends on the phase of something. And that phase can be chosen as the phase of some local oscillator. That is, in the optical context, a laser, okay? So that means that if we want to measure something relative to some phase, we choose that phase as the phase of the local oscillator, which is to say, in the quantum regime, we're inputting a coherent state into this port of the two-part beam splitter. This is the signal that we want to measure, and then we can look at a balanced, this is a so-called balanced Fomentine detector, as we discussed, which requires two detectors. That's a little more expensive than the unbalanced case. Maybe twice as expensive, or maybe more, I don't know. And yeah, there's a lot more work, but you get some benefit of it is that you don't have to control the noise on the local oscillator cancels out, okay? And you only see the beat note between these two, which is related to the quadrature along, that depends on the phase of the local oscillator, okay? And so if I were to look at the fluctuations in the signal, they would vary. If I have a squeezed input state, if this state was a squeezed state, with some squeezing zeta, then what we would see is that the noise would depend on the phase of the local oscillator, okay? So what this is showing us, what this means is that at a particular choice of phase, say the phase is here of the local oscillator, that would be the vacuum level. If I were to look at the photocurrent as a function of time, let's say it was squeezed vacuum, what I would see is something which, you know, would on average be 0, but would have some noise on it, okay? It wouldn't be exactly 0, and the fluctuations would have a variance of 1/2, relative to some definition of a mode, a temporal mode, okay? Whereas if we were at this case, what we would find is that the noise would be reduced. We'd have a much less noisy signal, and we would be able to tell 0 relative to something else much more, whereas over here, if I looked at the signal, what we would see in this case is noise that was much noisier in the antithesis, okay? So the noise is distributed in this phase-dependent way. Now we're going to talk a little bit more about this today. In particular, what we want to talk about today is how do we create such a state of light, okay? But before I do that, I just wanted to emphasize one thing that you'll see, if you haven't already started to do so, in your homework over the next week or so, which is this description of a phase-sensitive noise. It's kind of classical. We're gonna, there's a very subtle aspect in the sense in which a squeeze state is a non-classical state of the electromagnetic field, and the degree to which really it can be understood completely classically. It's kind of related, as we'll see, to a kind of hierarchy of different levels of non-classicalness. And what we mean by non-classical is a subtle point. You know, to some degree, it's relative to some definition we have of what that means. But we'll see that in more depth, okay? So, in what sense is the squeeze state non-classical? So I want to review some things we talked a little bit about last time, which is, you know, the generation of states of the field. Okay? So the fields are generated, they're radiated by currents. Okay? So, you know, the interaction Hamiltonian, the fundamental interaction Hamiltonian of quantum electrodynamics is the coupling of the current to the field, right? So that's equal to 1/c, integral over all space, the current dotted into the vector potential, okay, in some set of units, okay? So that tells me something about, if I start in some field, how through the interaction of the charges with the electromagnetic field, I would generate states of the field, okay? And in the, electric dipole approximation, if the currents are confined to a small enough volume and they're not moving that fast such that the wavelength of the light that's radiated is much longer than the size of the distribution, we can make a multipole approximation and approximate this as being due to the density of electric dipoles, say, if I have a neutral system or a system that's radiating. So P here, and this is P dot E, is the electric dipole density. Sometimes known as the polarization, but of course polarization has lots of different meanings. Okay. That's classical, minus. Okay. Now, what we discussed last time, or not last time, last semester, is that if I can treat the current rate of change of the polarization density, if I can treat the current classically, ignoring anything having to do with the quantum fluctuations, I can think about it as replacing it by the mean field. If that's the case, then, well, if I were to think about the unitary time evolution of this, that's generated by this Hamiltonian, it's going to have the form of something that looks like this. Sum over all the modes, sum alpha, a dagger. I can write it like this. Why does it have to have this form? Well, of course we know that the field itself is some sum over the modes, with something ak e to the ik dot r plus permission conjugate, right? And so this object is, for a classical current, is, if I have a classical current, then H, the interaction Hamiltonian, is linear in an A dagger. So if it's linear in A dagger, it has to have this form, right? Because it's got to be something which is anti-Hermitian, I times a Hermitian thing, and it's only got A's and A daggers in it, no products of A's and A daggers, okay? And this, of course, is the displacement operator associated with those complex amplitudes. So, importantly, if I have a classical current, if I start with nothing, the vacuum, then what I will generate, to the degree to which the current is deterministic, and I know exactly what it is some coherent state, okay? It'll radiate a coherent state. Of course, if my current is unknown to me, and I have a random but classical description of the current, then I'll end up with some statistical mixture of coherent states, which will have some P representation, which is the statistical mixture, the weighting of those amplitudes, but I will never get anything that is not a statistical mixture, okay? So if I have a classical current, more generally, with stochastic classical current. The most general state that I would have would be some statistical mixture weighted by the probability distribution that's associated with the current. Where this is some honest-to-God probability distribution. So the lesson that we've learned in the past and that we're reminding ourselves of is that if the source of the field can be thought about as a classical current, the state of the system must be of this form, okay? And what we also learned is that if this is true, that the fluctuations in the quadrature is always greater than or equal to a half for all phase. There's no way I can choose some quadrature which will have fluctuations less than the vacuum level, because I'm just going to get a statistical mixture of the fluctuation. I'll add together those variances and I'll never get something which has less. So what we have learned is that a squeeze state cannot be created by a classical current. So we need to think about some source that we would say is a non-classical source. It's not a source that I can think about as just oscillating dipoles. There's something sort of intrinsically quantum mechanical about the source that would be necessary in order to violate this assumption, okay? So how are we going to do that? So there are many ways we can think about it, but one way that one can start to think about how I might generate these non-classical currents is to use the process of nonlinear optics. We want to go beyond this linear description, okay? So the idea of nonlinear optics is that I can use high-powered lasers to drive current in a material that is not describable by linear response. I'll explain what that has to do with non-classicality in a moment, but what do I mean by that, by linear response? The basic point is the following. Let's say I have some material, a crystal or whatever it is, and I have this high-powered laser. We'll call it the pump, okay? And there's something going on in this material, whatever it is, which is going to scatter light. The pump light is scattered into other photons, into other modes. Those other modes could be other directions, they could be other frequencies, okay? We can, to the degree to which we can still think about this, even though it's not linear response, I can think about it in a perturbative way. I would say that the induced polarization density I might write in a power series in different powers of the electric field, to the degree to which it's maybe not just a linear response, but still perturbative. So I would say that there's something proportional to the electric field, which I'll call chi1. And there's no epsilon naught here. These have the same units. But then there's maybe some second order effect, and it depends on E and E in some tensor way. It might depend on the polarization. This is a kind of, I'm just being loose with my notation when I write two vectors next to one another. And then there'll be a chi3, et cetera, okay? So this is saying that I can, in some approximation, I can say that there is a Taylor series expansion which the induced oscillating polarization or dipole density has different powers in the amplitude of the fields, okay? Now, this response is linear optics. And the rest of this is nonlinear. Now, we want to first understand the classical nature of this kind of nonlinear optical process before we can get into the details of the quantum description of the nonlinear optics. If the system were described only by, if the response were only linear, then I'm not going to in any way drive non-classical current, right? Because photon by photon, I'll have some response, and that will just be some other linear transformation. As we've seen, and I'll remind us that when we thought about, for example, sending light through an interferometer, the way in which the amplitudes transform classically is the same transformation as we have on the creation annihilation operators. And there's no change in the photon statistics. That's a linear optical process. Okay? So linear optics, if I start with something which is classical in, and I have a linear optical response, I'm never going to have anything other than classical light out. Now, just a little aside here. One of the things that, of course, I always sort of learned this stuff as a graduate student, thing with that, it's like always, you can't do anything with linear optics. You got to have nonlinear optics to get to something non-classical. But, there's an important caveat in that whole thing, which is that the input state here is assumed to be classical. If I somehow, through some process that we'll talk about, created non-classical light, and then put that through some other linear optical transformation, that could be interesting. And the whole story of boson sampling, which you may have heard about as a way of demonstrating quantum supremacy, just a linear. It's the last place on Earth a quantum optician would have looked for quantum supremacy is in a linear optical network. I mean, that's the most classical thing in the world. But nonetheless, there's all kinds of interesting things, as we've seen a little bit, like the Hangel-Mandel interference effect, which is a linear optical effect, but nonetheless is very non-classical if the light that comes into that linear optical transformation is not classical light. So I just wanted to preface this, linear optics with, all right. Very good. So, let's see. Let me remind myself what I wanted to say next. Right. Okay, so generally, although I wrote it this way, this is a little bit of a lot of a shorthand, because as we know, the way in which a material, its dipole oscillations respond are very frequency dependent, right? So, depending on how fast the field is oscillating will depend on how fast the material can respond. So really we want to put all of that in. So in linear optics, I might write the positive frequency component. I'm going to leave off I'm going to treat this for some given polarization mode. I'll leave off the vector nature. The polarization at some position, I'm not going to write it as a function of time, in linear optics will be dependent on what the, well, maybe I'll put the position dependence in here. The susceptibility, the linear susceptibility, is as a function of frequency, okay? All right, so what about the second order, nonlinear term? Well, that involves two powers of the electric field, and thus there are beat notes between the fields that can depend on both the sum and differences in the frequencies of those two fields. So I'll have two frequencies. There'll be a chi2 coefficient that will depend on the particular frequency. For example, there might be some frequency, I'll call omega 3, which is the sum frequency of the two, and that will involve a term that, oh, yeah, of course, this, what did I mean to say in this case here? Excuse me. So this, what I wrote down here, no wonder I was confused. It doesn't make sense. Okay? Let me try again. This is the Fourier transform of that. Okay? This is just the Fourier transform of that. But this, in linear optics, is proportional to the electric field. Okay? So this is chi1 times the electric field strength at that frequency. Now it makes sense. Chi1 times E is the polarization. Okay? This guy will have two terms. I'm going to have the electric field at frequency omega 1 and the electric field at frequency omega 2, and the sum of the two. Okay? So there's going to be a term in the positive frequency component, which is the beating of these two, both the positive frequency components, add together to give a total frequency omega 1 plus omega 2. And I'm going to get, there's going to be other terms, though, which are the difference frequency. And that will involve one these being positive and the other one being negative, which means I have E star. everyone see that? That these are, when I write out the square of that, I'm going to get this term. Now, if the medium has a non-zero chi2 is going to be the dominant effect in this perturbative. So we'll just stop there for now. So what we see here is there is a some frequency term.
Zero frequency term under infinity. So it's omega 2 minus omega 2.
Yeah, I guess that is, yeah, that makes sense anyway. So omega 1 minus omega 2. Yes. And then I have a difference frequency. Okay. And this then is a source of radiation. So there will be a dipole density in the material that is oscillating at this frequency, depending upon the amplitude of the field at those two frequencies and the strength of susceptibility at the some frequency. There will also be a term that radiates at the difference frequency, depending upon the amplitudes and the strength of the chi2 susceptibility at that difference frequency, and you'll see radiation. So from classical electrodynamics, we can calculate the wave equation that tells me what is the radiated field associated with these sources. Okay, so the wave equation tells me that is related to the current, right? The source of the field is the current, and the current is the oscillating polarization density, and that gives me 4 pi over c squared, d squared by dt squared of the polarization density. That's the wave equation in my favorite units, which should be yours. Okay? So, given this, and given our decomposition where we write T as chi1 times E plus chi2 times E times E, if I look at this in the frequency domain, firstly, I see the following. So I take the Fourier transform of this and look at this in the frequency domain. This tells me right? And now if I write P tilde as chi1 at whatever frequency E at that frequency, plus chi2 at some frequency, I'm just going to call it for now, we'll come back to it, plus whatever P2 is due to the nonlinear effect. I put that in, what I get is omega, let's see, delta squared plus the index of refraction at that frequency, omega squared c squared d tilde r omega plus or minus omega squared over c squared 2, where the index of refraction is 1 plus 4 pi chi in these units, okay? That's the index of refraction associated with the linear part, the linear response here, okay? And this is the wave number squared, okay? So, let's see. Right. Okay, one more thing now. We make a certain approximation. So now what we're going to say is that the change in the amplitude of the field as a function of propagation distance is slow compared to k, which goes like 1 over the wavelength. That is to say that if this is a weak process, the amplitude is growing over distances slowly compared to the wavelength, which is a much faster scale, okay? That's just, again, about this being a weak process. In which case, I could make the well-known slowly varying envelope approximation, or SVE. We will write our, firstly, what we're going to think about is one-dimensional propagation. So we'll think about this as a kind of, not probability, but propagation. And we'll say along the z-axis. So we'll forget about the transverse diffraction, which think about it as a plane wave, but along the direction of propagation, there's some radiation. And we'll write the electric field amplitude as a function of z as some scripty e to the I kz, where the derivative of this respect to z, the magnitude of that, is much, much less than this. Okay, so if I didn't have any change at all, I just have a plane wave solution, for example, if there was no source term, I can think about a plane wave solution to the wave equation. But I'm going to have an amplitude that modulates this, which is going to grow in some way, but slowly compared to the wavelength. Okay? So if I make that ansatz, and I have this approximation, I can plug it in to the wave equation. So this, I just said it's 1D. I've made this ansatz. Now I'm going to use this approximation. When I take the second derivative of this term, well, let's just write it all out. So what I'm going to see in this case is I'm going to have d by dz squared of e tilde plus 2ik dE dz minus k squared That's the second derivative of this thing. Plus k squared e to the I k z. Right? That's just taking that second derivative. That's this term. This cancels, and we say this is approximately 0 compared to that. Okay. Similarly, we write the polarization density as script dp e to the I k z. Now, actually, I'm not going to do that because we'll see that and we'll put it in a different way. Anyway, I plug that in equal to the thing on, this is equal to minus 4 pi omega squared over c squared p tilde of that, which means that we get an equation of motion which says the rate of change along the direction of propagation of the amplitude is equal to I times 2 pi omega over c n over omega p tilde of z over omega e to the minus I k z. Right? That's just equating these two things and solving. So this tells me how the amplitude associated with this field at this frequency, which is propagating along this direction, is generated by the oscillating polarization at that frequency. Now, the polarization that's oscillating at that frequency is this, which is given here. Okay? So we can see from these expressions, thus, how the different nonlinear optics can be used to generate different frequencies that didn't exist before. And that's, that's how we get, new frequencies in lasers. We use one pump frequency and we generate others through nonlinear optical processes. Okay. So, for example, let's talk about some frequency generation.
Some as in SUM or some as SO?
The sum, as in add two things together. So let's suppose I have a material that has some good chi2, okay? And I send in two colors. Look how fancy I am. There's one color that's orange and another color that's red. They really are overlapping, but I don't want to show that. A lot. They're the same. It'd be very nice if they were exactly overlapping the same spatial mode. Okay? And let's say that this chi2 material has some good chi2 at omega 3, which is the sum of omega 1 and omega 2. Okay? All right, so that means that, somewhere in this crystal, I'll have an omega-3 generated as a function, and we want to find out what that is. Okay, and so we have that from this expression over here. We can just look at this expression and look at my notes and make sure I want to screw things up too badly. And what we would see, and now I'm not going to be that fancy, I'll go back to my monochrome world. Pi2 at omega 3, which is the sum of omega 1 and omega 2. And then I'm going to get an EZ at omega 1 and the omega 2 e to the I k 1 z e to the I k 2 z e to the minus I k3 z. Okay, so this whole thing was p tilde at omega 3. That's to say, the polarization density that's oscillating at omega 3 is the beat note between the two lasers at omega 1, the orange and red laser, which beat together. Okay? And then we had, I brought this onto the other side. All right, now one way we can solve this, at least approximately, I would have a separate equation which would tell me how the amplitude in the orange and red, let's say omega 1 and omega 2, are changing as a function of propagation distance. And I'd have 3 coupled nonlinear differential equations, which generally we can't solve, okay? However, we can solve this problem approximately under the so-called non-depleted pump approximation. So to the degree that we say that these guys are approximately both constant, that's to say, we're not depleting any of the light that's transferred from these modes to this frequency is so small that I can just keep the intensity of the red and orange light as constant over the propagation distance. Then I can solve this equation, and it's a good approximation, okay? And so under that approximation, what I have then is the following. The E tilde at frequency omega 3, just think about some notation here. Yeah, okay. So that's equal to this thing, which is, some constant e to the I delta k z, where delta k, or e to the minus I delta k, is k3 minus k1 plus k2. Okay, which is what exists there. Let's see, is that how I want to define this? I guess I want to define it the other way around, sorry. Just consistent with my notes here. We'll call that plus. And we'll say this is K1 plus K2 minus K3. All right, so with that said, under this approximation, then the amplitude in the sum frequency is equal to that constant. It's approximately equal to 2 pi omega 3 over c times n at omega 3, chi2 at that frequency, the amplitudes, which we assume to be independent of distance, times e to the I delta k L minus 1. This is at the output at L. Z equals L over delta k. That's just integrating that equation.
So, when does this actually occur? Like, when is the epsilon squiggle over dz? When does the non-depleted pump approximation actually?
When does it make sense?
When you have bad conversion.
Yeah, exactly. So it's really that chi2 is weak, so that little of the light is transferred relative, to its initial intensity. So in a very strong pump and a weak chi2, very little of the light is going to be converted from this to that.
Okay.
All right? So this non-depleted pump approximation is for weak nonlinearity. And this being big. Okay, and so the intensity at this frequency, at the output port, the square of that amplitude, is something squared, it depends on something squared, some constant, times the intensity in field 1, the intensity in field 2, times the sine KL over KL squared times the length squared. Okay. So one thing we see here is that the convergence of how much intensity I transfer from one to the other depends on delta K. When delta K is 0, then I get the strongest conversion. But when delta K is too big, then I don't get a strong conversion. Now, what the heck is delta K? And why isn't it 0? Delta K is equal to n at omega 1 over c, plus n at omega 2 over c, minus n at omega 3 over c, where omega 3 is equal to omega 1 plus omega 2, right? So why doesn't this equal 0? The reason is that this is a function of frequency. And so I generally, if I have one kind of mode, there's no way I can satisfy this, okay? And the process by which I try to choose this thing is called phase matching. That's this guy. Why is it called phase matching? The reason is that what I have is a radiated field that's propagating with some speed, right? It has some phase velocity, c over n. But this field is coming from the beating of two polarization waves. I have these two waves that are here, and they are generating a polarization density that's propagating like that. And the question is, does this stay in phase or not with this? Because if they get out of phase, I'm not going to amplify anything. Okay? So that's why it's called the phase matching condition. Now this is just a little aside. We'll talk more about this because it's important for some of the ways in which we actually make this light. How can we actually do this phase matching condition? It seems impossible. The way I can do it is by having the material which has a different index of refraction for different polarization states of the field. So I could have a situation where I'm generating, I start with these two colors of light that I put into this crystal, which are polarized in some direction, but have this light be polarized in this direction, and have the crystal be birefringent. Which has a different index of refraction depending if I'm pulling on it this way versus that way. This, by the way, I'm sure I'm drawing all over my, I guess you know I do that, is what's known as type 1 phase matching. Anyone ever heard of that? People who work in the lab must have heard of that. That's what that's about.
Today doing nonlinear optics.
Okay, well, all right, well, there you go. You get another version of it. Yeah.
The better ones.
Yeah, well, of course. And I could have a type 2 where I choose these guys to be in different directions. Anyway, that's neither here nor there, but it will be important for us when we start talking about the generation of squeezed light and entangled pairs to understand something about the polarization entanglement that we will see. So it's not just a bunch of details. It's going to be really important for how we generate and the nature of the non-classical light that comes out. Okay, finally, let's talk about difference frequency generation and the general problem of what's called three-wave mixing. So let's talk about the general problem of what's called three-wave mixing. Why is it called three-wave mixing? Because we got three waves and they mix. Those three waves are the waves that have a wave number K and omega 1, 2, and 3. And we want to write down the three set of coupled ODEs that describe this in the slowly varying envelope approximation and 1D. All right. So this is the equation I just wrote down, but I'll just write it again. Then I'm going to write down the equation of motion for the other two waves now. My notes look over here. this guy is at the difference frequency. And this guy okay, where omega 1 plus omega 2 is omega 3, and I'm also phase matched. So this oscillates at the difference between omega 3 and omega 1, which is omega 2. This oscillates the difference between omega 3 and omega 2, which is omega 1. And this oscillates at the sum of omega 1 and omega 2, which is omega 3. Okay? And what I want to study here, for example, is a problem what's known as parametric amplification and difference frequency. Generation. Now, I'm going to be a little bit more general here and assume that the two waves, omega K1 and K2, need not be co-propagating. I could have them co-propagating, but I don't have to. So for example, here's my crystal again. Okay? And what I'm going to do in this crystal is I'm going to have this strong pump at frequency omega 3. And then I'm going to have my signal propagating here. Okay? And this thing is going to be phase matched such that the sum of K1 and K2 is K3. Okay? The magnet. So what will happen in this crystal? This is strong. These two guys, what I'm going to end up with, depending upon, let's suppose that I have a strong effect here at both chi at omega 1 and chi at omega 2. I'm going to generate a third wave that's going to be generated, which has the name that I have no idea why. It's called the idler. It's just idle. I don't know why it's called the idler. There's a signal on the idler. They're always called the signal idler. One day I knew that, but I don't remember why it's called that anymore. Does anyone know the answer to that question?
Not exactly. I know it's from like RF engineering.
Yeah, it's an RF, it's a radio thing, right? This was three-way mixing in radio, but God knows why now. And I'm sure ain't God. Yeah.
Two questions with the equations you wrote. Are they also supposed to be derivatives with respect to time? Like so DE?
Oh no, they're all DT. I mean, they're all DZ.
They're all these Z's.
They're all DZs.
Oh, so two of them are wrong.
Oh, they're all DZs.
And then do you want E1 or sorry E2 star on the first equation, or sigma 2 star, epsilon 2 star?
These guys.
So it's sum versus difference.
This guy. This is correct because
Oh, one.
these guys
Oh.
add and these guys subtract.
Gotcha, sorry.
Yeah. Yep. No, but good. I'm glad you asked. Okay. So what's going to happen in this process is twofold. One thing that we're going to see is that we're going to transfer some of the light from the pump into the signal. And I'm going to amplify this, okay? That's to say, I put in some field here, and some of the energy from this frequency is going to be transferred into this frequency and grow the amplitude, and that's known as parametric amplification. The term parametric, well, we'll understand why it's called that in a moment, okay? At the same time, I'm going to generate a third wave, which is the frequency difference. So this idler is at the difference in the frequencies between omega 1 and omega 3 and omega 1. I'm the least ambidextrous person you know. I don't know how I do it, but I really cannot do it. I come out and chop the left hand off. That's the difference. All right. Right. So how do we see that? Well, the first, one way to solve this problem again, which is an excellent problem, approximation, is to use the non-depleted pump approximation. So we're going to assume that this is a constant, that this is not, the amount of energy that is taken away from this pump is so small that I can just treat this pump as a constant. In which case, this equation doesn't matter, and I treat these guys as constants. Okay. So, with that kind of equation, what we see in this case then is that these equations take on the following form. Right? That looks familiar and nice to some of us. We have this coupling between that and its conjugate, right? Where this, I'm treating this whole thing as kappa 1, and this whole thing as kappa 2. So now I have a couple set of linear ODEs. They became linear because I made the non-depleted pump approximation. How am I going to solve these equations? Anyone have a suggestion? Yeah, I'm listening.
I said give up, but.
No, that's not the answer. Not
Well,
even.
actually has the answer.
So we have these complex numbers. If you look at the real measure marks, but first we have to know how factors are complex.
They are
We should
complex.
Split those as like some
Yeah.
modulus times.
I can certainly do that, but I have a sort of simpler, quicker way forward here, which is, let me take the second derivative. Right? And then I can plug that in. Now this is a K1, kappa 1, which is equal to kappa 1, kappa 2 star times E1, right? Now this is a real number because they're both I. So this is equal to the magnitude of this times the magnitude of that, which I'll call kappa squared. Don't give up. Take a second derivative. All right, good, we did that. So what we have found, and what's the equation motion for the other guy, by the way? If I look at the second derivative of E2, I'm going to get kappa 2 the derivative respect to z of E1 star, which is kappa 2, kappa 1 star, E2, which is the same kappa squared E2, right? And I just broke this. Okay, so the equation of motion I have then is that this minus kappa squared E1 equals 0, and the same thing for frequency 2. What is the solution to that? Oh, it's the second derivative. Right? It's Cauchys and Cinches or exponentials, you name it. Oh, Cauchys and Cinches. Oh, that seems familiar, doesn't it? So this says that E1 at Z is equal to E1 at the input cosh of kappa Z plus E1 derivative at 0 divided by kappa sinh. That's the solution to that differential equation given the two initial conditions on the initial thing and its derivative. Because we know how to solve differential equations, don't we? And so that's equal to E1 at 0 cosh kappa Z, and then the derivative of that is equal to kappa 1 over kappa times E2 star at 0 sinh of kappa Z, where kappa is equal to the magnitude of K1 times the magnitude of K2 square root. Kappa 1 or 2 is given here as I 2 pi chi 1 or 2 over C n 1 or 2 times E3. Okay. And similarly, we have the same kind of solution for E2 at Z, which is E2 at 0 cosh kappa Z plus kappa 2 over kappa E1 star 0 sinh kappa Z. Okay, so notice these are Bogoliubov transformations. I mean, it's a two-mode Bogoliubov transformation that's more analogous to what we're seeing in the two-mode squeezing. This actually does create a two-mode squeeze state, as we will see. But right now, we're just thinking about this in the notion of parametric amplification and difference generation. So if at Z equals 0, we have no orange light coming in, then the red light at that frequency be amplified. It'll grow like cinch, okay? And this guy over here is going to be kappa 2 over kappa E1 star. Times cinch. So this is parametric amplification. And this is phase conjugate amplification. That is to say, the idler field is the complex conjugate of the signal. That's a useful thing in some applications to have access to the conjugate field. But that's actually what comes out of this. But we notice these equations of motion, as we'll see, are the equations of motion that are equivalent to the Heisenberg equations of motion associated with the squeezing Hamiltonian. So there is some intimate relationship, which we'll get into more and more, between nonlinear optics in the non-depleted pump approximation, where we've effectively linearized the problem. But not exactly linearize it, because we have this coupling to the conjugate field that leads us to squeezing. It's very, the story of parametric amplification has many layers to it, some of which are classically understandable and some of which are not. So we're going to unfold that story a little bit, some of which you'll see in your homework, some of which we'll discuss here. Okay. All right. All right, let's call it quits, and I'll see you next time.